Welcome to Chapter 13, which is our chapter on graphing. Although we're going to cover the techniques and the concepts of graphing generally shown with a paper and pencil, what I recommend you doing is work through the video that I've given you on graphing and charting using Excel. It's a lot more accurate, and you learn some more Excel skills. So we're going to look at plotting points on rectangular or the Cartesian coordinate system, looking at linear equations and graphing, understanding the slope of the line and the line intercept form using the equation of the line y equals mx plus b, and plotting curves. So our objectives follow along just exactly what I said. A graph illustrates the numerical relationship between variables by plotting points on a graph. And this is your traditional graph that you would see that had an x and y axis, squares on it that are all of equal sides. The most commonest type of graphs then are the grid of horizontal and vertical lines. On this one, there are no specific graduations. We will see later that we will mark the graduations accordingly. And using a piece of graph paper like this, you can change the scale. For linear graphs, the spacing between the horizontal line is constant and represents a defined change in the variable represented on the vertical axis. And so we'll start to see later how we plot on these using something called independent and dependent variables. So the system of rectangular coordinates, the Euclidean or the Cartesian graphing looks like this. You can see that we've added some additional lines in here to understand that we can create quadrants. In this case, the first quadrant, second, third, and fourth. This is a standard division of the quarters on a piece of graph paper where we have the origin at the center and the x and y axis forming the overlap of that origin. So the graph of any linear equation is a straight line. We have terms that we need to get used to: the x-intercept, the y-intercept, the coordinates, the abscissa, and the ordinate. The x-intercept is the point where the line crosses the x-axis or the horizontal axis and is consequently the point's y-value becoming 0. The y-intercept is the point where the line crosses the y-axis and consequently is the point's x-value as 0. The coordinates then is the set of numbers x and y that forms a location of a point on the plane. The two other terms, the abscissa and the ordinate, the x-coordinate of a point, which indicates the distance and direction of the point from the vertical axis, becomes the abscissa. The ordinate then is the y-coordinate on a point, which indicates the distance and direction of the point on the horizontal axis. And these will become more important to us as we do graphing, but as we start getting into complex numbers and in electronics, doing vectors and phasors. So if we take a look at an example here, an equation 2x minus y equals 6, let's take a look at inserting some values and seeing how we can plot the coordinates then on a graph or a chart. So with that equation, let's say if we we're choosing a value, we're going to let y equals 0 in this case and solve for the expression or the equation. So if I put y in here as 0, I end up with just 2x equals 6, and therefore when I solve for x, I get x equals 3. So in this case, all I would have to do is come down here on the x-axis, place a dot there, and that would be my x point for 3 and 0, x and y. Now if I say I'm going to let x equals 0 this time and solve, I end up with the expression of minus y equals 6, or moving the negative sign to the other side, y equals minus 6. So now I have my 0 and minus 6 values. With just those 2 points, I could put a ruler on here and plot that line from end to end, and then extrapolate any values in between or beyond the points. So at this point, if I said, okay, well, what if I just let y equal 4? So if I say y equals 4, I insert that into the equation, I get a value of x equal to 5. And then repeat it one more time, x equals 2. Solving for y this time, I get y equals minus 2. So by just choosing values, I can determine graphically what the set of ordinates or coordinates are that solve the equation 2x minus y equals 6. The slope of the line. The slope of the line is a set of values then that we pick off of the line, the equation, from the equation of the line that we just solved for. So in this case, we're going to look at the change in values from x to y, or y to x. You must have more than one set of coordinates in order to solve for the slope. The slope of the line then is defined as the change in a y value that results from an increase in the x values. Sometimes we call this the rise over the run. So mathematically, the slope is equal to delta y, or the change in y, divided by the change in x. And so if we just pick values here and say, well, okay, what is the slope here given a value of the change in y being 4 and the change in x being 2, we end up with a slope of 2. So if we track that rise over the run, up 4 over 2, up 4 over 2, we would end up with our slope value that characterizes that line and the angle that it makes, or the slope that it makes. If a linear equation contains 2 variables, then we can write it as y equals mx plus b. Y equals mx plus b then is our standard equation of the line. Y and x are the variables, m and b are the constants. So in this case, looking at that equation of the line, if we have x and y as our variables, m must be characterized as something and b must be characterized as something. And what it is, by definition, m is the slope of the line, y is where we have a y-intercept, or b is the y-intercept. So if we look at an expression given the equation 3y minus 2x equals 9, find the slope and the y-intercept. So we're solving for m and b. So if we look at this expression, 3y minus 2x equals 9, the first thing we need to do is start moving some terms around so that we have it in the form y equals mx plus b. So in doing this, we're going to set it up y equals something times x plus a value that becomes b. So what I'm going to do is I'm going to divide the whole right side of the equation by 3, which will let the y value stand alone with no coefficient, and I end up with 2/3 x plus 3. Now I have simplified it to the form y equals mx plus b, and I can glean out the value, the slope, m, as 2/3, and the value 3 as the y-intercept, or b. So you notice we had to isolate on either side of the equation the y by itself before we could solve for the rest of the terms. In interpreting graphs, we need to plot values. In this case, very typically, we have a current variables on the y-axis. We have the voltage variables on the x-axis. And what it really corresponds to is this simple circuit we see on the right, where we have some resistance value and a variable source where the source goes from 0 to 20 volts. And so as we crank up the voltage, it's going to increase the current, and we will find that the resistance becomes a steady or a constant value. In this case, that resistance is related to the slope of the line. So from the graph, we can see that resistors are linear devices. As we increase the voltage, the current goes up, but this line itself, the solution, becomes a straight line with some slope. And so if we solve for that slope, the graph shows us that the current versus the voltage graph gives us a constant value of resistance, 1 k ohm. Okay, so if we plug our values in here for the slope, a change in the current, 4 milliamps, the change in the voltage, 4 volts, gives us a conductance of 1 millisiemens. We need to do an inversion, so R is equal to the reciprocal of 1 over G, or that value, and we see that the voltage and current yields then a constant resistance of 1 k ohm. So graphically, we were able to determine what we expect the result to be, a constant resistance, by changing the voltage and the current. Again, we have those dependent and independent values. Another type of graphing, in interpreting the graphs, is not a straight line, but something we call a nonlinear devices. A nonlinear device will give us this curved line instead of a straight line. And so as the voltage increases, the current non-linearly responds to that increased voltage. The difference in this one is we cannot track the slope based on the curve itself. We have to do something different. And the something different we have to do is we have to place a line tangent to a point that we choose on the curve, and then from that value determine the slope of the line. So we are determining the slope based on a single point in this representation. So the most accurate method of determining the slope of a curve then is to select a point on the graph and then construct a line tangent to that point. So we will have picked a point right here on the curve, draw a line tangent to it, and then we would start to select or map out determining our values for the slope. So in this case, in the x direction, or in the voltage direction, a change in 0.3 of a volt on the x-axis yields a change of 8 milliamps of current on the y-axis. So you can see it's a little bit different in looking at the linear device. So when we solve for this slope of the line, we end up with the change in current divided by the change in voltage. 8 milliamps divided by 0.3 of a volt gives us 26.7 millisiemens of conductance. So in this case, we have two different factors. One is based on what's called a dynamic resistance, and one is actually an instantaneous value called the DC resistance. So the dynamic resistance, little r, little sub d, is equal to the inverse of the slope, 1 over. So we can take that value that we calculated, 26.7 millisiemens, and do an inverse on it, and we get a dynamic resistance of 37.5 ohms. If we pick one point, though, on the line, this becomes the DC resistance, and you'll notice that the DC resistance gives us a much larger resistance value. Again, this becomes the instantaneous value for that resistance. In interpreting graphs, then, the nonlinear device then can be characterized by those two resistances whose equations we just saw. You'll notice the DC resistance is just picking two values on the line. The dynamic resistance actually requires us to look at the change in those values. As the voltage increases, the current changes, and that gives us our dynamic resistance. Another curve set that you will be using as you get into the preceding courses, ET131, 132, is something called the time constant chart. And a standard time constant chart looks like this. You've got two sets of curves that is showing you time constants values and the percentage of value based on a voltage across a capacitor and voltage across a resistor. A universal time constant chart then is an RC circuit has one time constant equal to the product of R and C. Okay, the time constants then are plotted along horizontal lines, and the applied voltage is plotted along the vertical lines. So you'll see more of this as you get into the DC course and you start calculating RC circuits that have DC charging going on. In plotting curves, then, if we go back to that circuit we had before with the variable source, this time we're looking at a value where we are plotting then an understanding of the independent and the dependent variables. So in plotting this graph, you can see that on the x-axis we have voltage. That becomes our independent variable. Generally, that's what we're going to increase, as you can see from the source over here. As we make the increase, the dependent variable, or the variable that tracks or corresponds to the independent variable, is our current. So as we increase the voltage, we're going to increase the current in response to that. Again, we rely on the same relationships for determining our slope and the resistance, and it comes back to what we've already seen. The slope corresponds to the conductance. The inverse of the slope corresponds to the resistance. Finally, we can take a look at in plotting curves. We typically will set up an array. You can see from the chart over here, we have an array of voltage versus current. And as we start plotting our values by putting the selected values into our relationship, or we actually make some measurements, our slope again becomes the change in current with respect to the change in voltage. So if we said, let's choose a value of 2 volts as our change in voltage, our corresponding current would be 200 milliamps as plotted, or microamps as plotted on the graph here. So we set up our slope relationship. We end up with 200 microamps by 2 volts, and we get a value of 100 microsiemens. If we invert that, we end up with an inverse slope, which is 1 over G, or 1 over 100 microsiemens, and we get a resistance of 10k ohms. So in graphing, it helps to understand what we're looking at, especially when we start doing measurements in circuits and we try to characterize what we're seeing in a graphical representation. As I said, what I would like to see is you using Excel and the chart function in there to graph this, because it has some very clever wizards in there that help you to create a very accurate graph instead of pulling out a piece of paper and a pencil and trying to plot points. If you do the graphical tutorial that I provided for you, you get a quick solution and understanding of using Microsoft Excel to do these functions.